talk some of these properties more in detail and see what they are and what their molecular origins are and how they may be seen in future classes and also in this class. So viscosity, this is basically just the resistance to how things flow. And I'm going to just warn you a little bit. I'm going to show you a derivation, very simplistic derivation of viscosity that's got mathematics embedded in it. I am not going to ask you about this in this class. I just want to show you where it comes from, and so you have a better understanding of what viscosity is. So imagine I have this guy in a swimming pool, and he's sitting there on this floaty, and then I have a fan that can blow on the water and move him. Okay, and I want to move him at, say, 5 miles an hour, whatever. And I can change the speed at which this fan is spinning, and then when it's spinning faster, it will have more force on the water, and it will exert a pressure, we'll say. A force over an area of the pool, and it will exert a pressure, okay? And the force or the pressure that I'm applying onto this guy is only going to be at the top layer of the pool, right here, at the top layer, okay? And another thing you should know is that the bottom of the pool is not going to move. Okay, and the distance between the bottom and the top is, say, y. Okay, so if I want to move faster, what can I do? Well, the faster the force, the pressure, the faster I'll move. So that's pretty obvious, I think. The pressure is proportional to the velocity. So the faster the force, the faster he'll move due to a stronger force or pressure. Okay. What about the depth of the pool? Well, since I'm really only applying to the top layer, and the fact that the bottom of the pool doesn't move means that the deeper the pool, the easier it is for me to move him. Why? Because the bottom of the pool resists movement. So the water that's touching the bottom of the pool is not going to want to move as much, and it's going to be more difficult for me to move the top layer. The top layer in this scenario, where it's deeper, is actually going to move faster because it sees the bottom of the pool from much farther away. The effects from the bottom of the pool are less felt in this scenario than in this scenario. So I'll say that the depth of the pool is inversely proportional to the pressure. And think of oil flowing down an incline, if you can imagine it. The top layer of the oil will move, the bottom will stay intact, and will just stay touching the ground. And this is the reason. Okay, what about the fluid itself? So you know this probably intuitively, that if I made this honey, it will be harder to move than this. So there's this magical thing we'll call X that will resist the movement. Okay, and X is stronger for honey than it is for water. Okay, turns out that this is Newton's law of viscosity, and I can translate that into the actual equations. Don't worry about this. This is the actual variables that deal with it. This X factor that I just mentioned here, that's known as the viscosity. And that's all it is. And it's just resistance to flow. Honey has much stronger intermolecular forces than water. Much stronger. And so honey has a higher viscosity and more resistance to flow. The stronger the molecular forces are, the more the thing looks like a solid. The weaker they are, the more they look like gases. Okay, and that's why honey has a higher viscosity. It feels more like a solid. It resists flow. Solids don't flow. Okay. Again, I will not put these equations on the exam. I'm just going to ask you, hey, here is molecule A and molecule B. Which one has a higher viscosity? That's it. I just want to show you where this comes from. Okay, very intuitively. You will see this if you take fluid mechanics. I promise you. But you're not going to see this here. Okay. So again, the stronger IMF, the higher the viscosity. Don't even worry about the units. We're not going to use them much. It's Pascal second or kilograms per meter second. Don't worry about it. We're not using it. Just want you to know what viscosity is and where it comes from. Okay. Another thing that I'm not gonna, I'm gonna show you an important. This is very important. I'm not gonna mathematically quiz you on this, but it's very, very important because a lot of people don't understand the origin of surface tension, and I think it's very important to understand it. So imagine I have a bunch of liquid molecules in a container or something, right? And there's more at the bottom, but there's no more at the top. This is the surface. This is the top of the cup. Okay, so I have a cup, and at the top of the cup, I have some water molecules. Okay, so what happens is, let's focus on two molecules, A and B. Okay, what you can see is A has 6 neighbors around it. Let's go back here. You see it's got 6 neighbors around it. B has 4. Okay, what this means from a force perspective, that this, if imagine it's a person, and they have hands, they have legs, and they have, I guess, 2 more hands, and they're holding hands and legs and 2 more hands with people around them. So imagine you're holding hands with 2 people, and they're pulling you in this at the same rate in both directions. You're not going to move. The forces kind of cancel. So this is what happens. This cancels this. This cancels this. This cancels this. A doesn't move. B, on the other hand, which is at the surface of the molecule of the liquid. Okay, so take a cup of water. Look at the top. That's the surface. The surface of the liquid doesn't have these 2 extra hands. What does it mean? Well, these 2 will still cancel, but these bottom ones will pull the whole thing down. Okay? Because they're pulling down, and B is still holding hands with its nearest neighbors, what happens, imagine yourself, imagine you are holding hands with someone, with 2 people, and then someone comes and pulls down on your legs, but you're not letting go of your hands. Someone is pulling down on your legs and you're not letting go. So you're still holding hands, and someone is pulling really, really strongly. What happens is, you feel a strain right here. And the stronger they pull, the more of this strain you feel. Like your hands will get tired. Your arms will get tired because you're holding hands. You're going to feel a tension, sort of like a wire. And you'll have a wire tension effect right at the surface. And this is what surface tension is. Okay, that's all it is. It's sort of like how much of a taut wire you have at the surface film of a liquid. And as you can see, the stronger the pull downward, the higher the tension. So strong intermolecular forces lead to high surface tension values. Okay, so things that don't have strong surface tension are going to be things like non-polar, like oils. Oils have very low surface tension. Water, which is very polar and has hydrogen bonding, has very strong surface tension, very, very high surface tension, about 3 to 4 times as high as that of oil. And it's because of the pull that water has from underneath it. Okay. Another thing to think about surface tension is sort of the energy that I require to separate this cylinder into 2. Okay? I have a cylinder, and I can come with like a saw here and split it in half, or not in half, whatever, any wherever I want. And the energy I need to apply, imagine like I'm manually cutting this thing with a saw, the energy I need to put into this is going to be much more if this thing is tightly packed together. Okay, and then if it was just like something that's very weakly bound, then I can do it within a second. If it's something like a metal, that's going to take forever to cut through it, right? That's sort of like the surface. That is surface tension, the energy to cut a liquid into 2 areas. It's the work required to get 2 new areas. And this is the equation behind it. Just like this, the work I need to create 2 new areas, this is the area of the circle, and the proportionality constant is the surface tension. The higher the surface tension, the harder this is. Okay? Again, I'm not going to ask you to apply this. I'm just showing you this. All I'm going to ask you is, Here's molecule A, here's molecule B, which one has the highest surface tension? That's all. I just want you to understand where this comes from. Okay? Another thing that you should know is that surface tension decreases with temperature. The higher it is, the temperature, the stronger, the higher the temperature, the weaker the intermolecular forces are. The more you look like a gas, the weaker the surface tension is. Okay? And again, it's increasing with higher intermolecular forces. Okay? Volatility, very briefly, it's how things want to vaporize. Do they want to vaporize? Okay? It doesn't have to do anything with boiling point. So, let's say I have a cup of water, and I have a cup of acetone or nail polish remover, and I put them side by side, or alcohol or something like that. I put them side by side. The alcohol will evaporate quicker than the water. So we say that alcohol has higher volatility than water. Okay, so this is the opposite here. Here, the volatility decreases with increasing intermolecular forces. Okay. Okay, so let's. Last one's boiling point and freezing point. These increase with intermolecular forces as well. Okay, because molecules that have strong intermolecular forces need more energy to make them melt and vaporize. So, if I want to know if something has high intermolecular forces, I look at the standard state for it. So, for example, a metal like aluminum has higher intermolecular forces than, say, oil, because oil is a liquid. And oil has stronger intermolecular forces than, say, oxygen, which is a gas, because they can bind themselves as tightly at regular conditions. Okay? And let's look at some examples here. So, which of the following, which of the following decreases as intermolecular forces are increased? And it'll be a multiple choice. So we have viscosity, volatility, the boiling point. Oops, I made this D. It's going to be surface tension. And E is going to be the melting point. Okay, so the answer is going to be volatility. Everything else increases with intermolecular forces. Okay, and again, increase in intermolecular forces, it looks more like a solid. Decrease in intermolecular forces, it looks more like a gas. And so you can see this here too. The higher viscosity, the more it resists flowing, the more it wants to look like a solid. The lower the intermolecular forces, the lower the viscosity, the more it looks like a gas because it wants to flow even more. Surface tension was that pull downwards. And the pull downwards wants to look more like a gas when there is no pull. When I have a lot of pull, an infinite amount of pull, I have a solid. So much pull that it's just pulling and freezing it in place. Boiling point and melting point as well are a measure of how strong the intermolecular forces are. So volatility decreases. Volatility is the opposite. Okay. Let's do another one from before, just kind of to put this in perspective. Organize the following in order of increasing boiling point. Okay, and I'll give you 4. Water, ammonia, methane and ethane. And ethane looks like this. Okay. So the way I would do this is I would first classify them as polar or not polar. So this thing here is polar. This thing here is also polar. This thing is not polar, as I showed before. This is also not polar. It's symmetrical. In all proportions, it's just symmetrical. Okay. So, in order for me to organize them, I have to recognize that these here are going to be dipole-dipole. Both of these. And these two are going to be dispersion. So right away I know that H2O and NH3 are going to be to the right. They're going to be stronger. Okay. So I'm going to have to compare them separately. So which of these is stronger, and then which of these is stronger? Okay. So how do I define? How do I determine here within here which one is stronger? It's the higher molecular weight. So let me just get the molecular weights real quick here. The molecular weight for water here is 18. For ammonia, it's 17 about. For methane, it's 16. And for ethane, it should be 30. Okay. So I'm going to compare these two. Which one is stronger? This one is stronger. So methane is going to be the weakest. So I'm going to do this here. This is going to be a final answer. Okay, so it's going to be increasing IMF, or sorry, increasing boiling points, the same thing. The weakest one is going to be on the left. The weakest one is by this analysis CH4, because the weaker of the dispersion. Second weakest is going to be this one because it's still dispersion. Dispersion is weaker than anything that's dipole-dipole. So CH4 CH3 CH3. So methane, ethane. Then I have to determine here which one is stronger. Well, again, look at the molecular weight. Water has higher, so that water should have the higher boiling point. So ammonia is going to be number 3, and then water is going to be number 4. And indeed, if I look at the actual boiling point, if you actually go and Google it, you find that the boiling point for this is negative 162 degrees Celsius. This one is negative 89 degrees Celsius. So these two are gases at room temperature. So is this, negative 33 degrees Celsius, and this is 100 degrees Celsius. Okay, so even though they both have hydrogen bonding, water has much stronger hydrogen bonding than ammonia, because O has stronger hydrogen bonding. Okay, hopefully this makes sense.